Hello, welcome back to CSE Core Concepts. In this video, I am going to discuss about a very interesting sorting algorithm called as a heap sort. Now, this is the sorting algorithm which uses the binary tree to perform a sorting. Now, first let us understand the meaning of the word heap. Heap is basically a data structure where you are going to place all the elements, of a list, but the structure is a binary tree. Now there can be two types of heap. One is the max heap and one is the min heap. Now max heap is when if the root element has the highest value, out of all the elements, whichever is the maximum value of the element, that is the root element. So if your root element is the maximum among all the values as compared to your left and right child, it is called as a max heap. And in case you are placing the root element as the smallest element, among the left and the right child, then it becomes a min heap. So basically what is a binary tree? Binary tree is a tree where it can have at the most two nodes, two child nodes, right? It can have either 0, 1 or 2, but not more than 2. So this is the example of a max heap and a min heap. So in the first example, you can see 95 is the highest among all the values. So it is placed as a root node, that is 95. And the same values when they are placed is using a min heap. 15 is the smallest among all the values. So 15 is the root node. Now the approach which I am going to use here to teach will be using a max heap. So we assume that the root element is the highest element. So what we basically do in case of a heap sort is that we construct a heap by treating the array as a complete binary tree. So what do you mean by a complete binary tree? When all the nodes have exactly two children, they are called as a complete binary tree. And since it is a max heap, the root element is going to be the highest or the maximum among all values. So we are going to replace the root element with the lowest value and then again going to create a heap. So this way we will go on replacing the last element with the root element until all the elements have been moved to the root. That means each element will go to the root at least once. So basically first let us understand. So we are given an array of let's say 9 elements here and the values are in an unsorted order. Now first thing is what I want to do here is that I want to create a max heap. So as I told you what is a max heap? That the highest value will become my root element. Now in order to create a max heap here, which is the highest value among all the elements here, that is 70. So 70 is placed as a root element. On the left hand side I am placing the first element, that is 62, on the right hand side 63. Since it is a complete binary tree, it will have two children, right? So one element will be placed on the left, another element will be placed on the right hand side. Fine. Then again 54 is placed on the left hand side of 62, then 30. Similarly 44 and 52, right? And then comes your 27 and 46. So out of these elements I just created a max heap. Now this max heap, what I will do here is that since the elements, now one thing I need to take care of here is that the root element should be highest among left and right. So at every subtree also you can see the root element is greater. Let's see. If you consider the left subtree where the root is 62 and its two node children are 54 and 30. So both 54 and 30 are smaller than 62. Understood? Then again you go to the left subtree, that is 54, 27 and 46. So 54 is the root node which is greater than 27 and 46. Now come on to the right subtree. You can see here that 63 is greater than 44 and 52. Understood? So this is how we are creating the max tree. This is called as a max heap. Now you realize that the first element, that is the root element 70, is the greatest. So what we will do here is that we are going to swap 70 with we are going to bring the last element. Who is the last element here? 46. So 46 will go to the root place, right? So we are going to replace it with the last element of the hoop. And 70 will be placed at the sorted array, at the last position. So just look at the array. At the last position, I am placing the highest element. Who is my highest element? 70. That is the root node. So now root became vacant. What am I going to fill the root with? The last element of the tree. Who is the last element of the tree? 46. So 46 is placed as the root. But does this satisfy the max heap condition? No. Right. Because 46 is smaller than 62, 63 and all. Right. So again I need to heapify. This process of creating the max heap again is called as heapify. So I am going to heapify. So while heapifying, what I realize is that 63 is greater than 46. Understood? So I will swap 63 and 46. So you can see on the right hand side 63 becomes the root node and then comes your 46 on my right hand side because I swapped them. Still, if you realize this tree, it is not completely a max heap because if you look at the right subtree from 46, 52 is higher than 46. That means although 46 is the root node, but it is having a smaller value than 52. So what I need to do here is that again I need to heapify where I am going to swap the positions of 52 and 46. Right. So now I get a max heap. Right. So 63 as the root node is the highest among all the values. On the left hand side, 62 is the root node for, among 54 and 30, which is greater, and 27 is smaller than 54. Done. On the right hand side, 52 is greater than 44 and 46. So now it satisfies the max heap condition. So next step is what? I am going to remove the root element, place it in the sorted array and replace the root with the last element of the tree. So who is the last element of my tree? 27. So I will simply place 63 as the second last position. 70 has occupied the last position. And now I am going to replace the value of 63 with the last element it was, that is 27. Now again we come to the same iterative step, that is this binary tree does not satisfy the max heap condition because 62, 52 they are greater than 27. So who is greater? 62 is greater than 27. Of course 52 is also greater than 27, but 62 is greater than 52, right? So the maximum position will go to 27 and 27 will come to 62 position. So 27 and 62 are swapped, right? But again, if you realize on the left subtree that 54 is greater than 27, right? So what I need to do here is that 54 has to be swapped with 27. There is no such criteria that the left side should be smaller than right side as in case of a binary search tree or something. Here it is simply like by other trees, right? Simply here it is like that the left and right element should be smaller than the root element. Now left can be greater than right, right can be greater than left, that does not matter. Okay. So here 54 and 27 again have to be swapped. So now this becomes my max heap tree. Fine. So next what will I do? Again remove the root element and store it in the sorted array and put and replace it with the last element. Now who is the last element in my array? 46 is the last element, right? So 46 will go to 62 position and 62 will go to 6th position of the sorted list. Now again if you see realize this is I have to heapify again because both 54 and 52 are greater than 46 and among them 54 is greater. So 54 will and 46 are being swapped. Fine. Now do I need to heapify again? 46 is greater than 27 and 30. Left subtree is sorted and 44 is less than 52. Again it is sorted. So I don't need to heapify again. It is done. So next step is what? Again I need to take out the root element and place it in the sorted list, right? And 54 will be placed at the 5th element and the last element was what? 44. So 44 will take place in the root position. Done. So again do I need to heapify? Yes, because 54 is greater than 44. So the position of 52 and 44 will be swapped. I hope it's clear. Again now it is heapified. Max heap is done. So I have to replace the root element 52 and I will place it at the fourth position, right? And with whom I am replacing 52? Last value. Who is the last value here? 30. Because root, left and right? So right position, that is 30. So 30 has become my root element now. Do I need to heapify? Yes, both 46 and 44 are greater than 30, right? So 30 and 46 will be swapped. So now, do I need to heapify more? No, because 30 is greater than 27 and right side has only one element, 44. So again, I will replace the root node 46 and place it at the third position of the sorted list. And 30 and who will replace the root position? Last element. Who is my last element now? 27. So 27 goes as a root element and 46 joins the sorted array list. So now it is hippified. No, because I have to hippify because 44 is both 30 and 44 are greater than 27. So 44 and 27 are going to get replaced. Done. Now they are hippified. Both 30 and 27 are smaller than 44. So what will I do? I will replace the root element, put the root element at the sorted array list and remove the last element, that is 27. Right? So 27 is being replaced here. Fine. Root element has gone. So 30 is there. And finally, 27 remains. Right? So you could have eliminated the 30. So 30 has been eliminated here. And there we have swapped it, because what happened here? When you remove this, only two elements are being left. Understood? Now what we did? 30. 30 is what? Greater than 27. So 30 and left side is my 27. Okay? Because this is what the array the list was being formed. When you removed 44 and 27 took the place of 44, it became a root node and on the left hand side 30 was there. Now 30 is greater than 27, so it will just be swapped. Understood? Now 30 will join the array, right? So only one element is left, that is 27, and 27 will join the sorted array list. So I hope it is clear to you all, right? Now again here, what is the condition? What is the time complexity? Time complexity is n into log n to the n to base 2. Why? Because for heapifying, first initial heapify, you have to go through all the elements, right? And then you are going to simply make it half and you are going to you divide at each iteration, the list becomes smaller. So for heapifying, you are going to concentrate on all the elements. So the time complexity comes out as n into log n to the base 2. So I hope you understood this heap sort. And in the next sort in the series, we are going to discuss about radix sort. So please don't forget to like, share and subscribe if you like the video to CSE core concepts. Thank you.